All right, so welcome back to Chapter 2. We are now ready to take on acceleration. We have defined position using either distance or displacement. From distance and displacement, we have defined speed and velocity. And so the time has come for us to discuss acceleration. Now, acceleration is defined as how velocity changes with time. And now, of course, as we ended our last video with, we mentioned that speed is the absolute value of velocity. So, oftentimes, whenever you are changing your velocity, you're also changing your speed. However, that's not always the case. Because direction matters for velocity, but not for speed, there are ways in which you can change your velocity without changing your speed. Because if you're just changing velocity, remember velocity has two parts being a vector. It has magnitude and direction. So acceleration can actually change either of those, or maybe even both. So you can change your amount of velocity, speeding up or slowing down. That can be an acceleration. But alternatively, you could just change your direction. That is also an acceleration. Whenever you turn your car left or right, you're changing the direction of your velocity. And if you're changing your velocity, you are accelerating. So, because acceleration is based on velocity, it is also a vector. The direction matters. And if you don't trust me on that one, well, if you're driving your car and you accelerate, you may think acceleration only means going forwards, but deceleration or braking is also a form of accelerating. It doesn't always have to be referred to as deceleration. That could just be negative acceleration. So, if you're in your car, which way you accelerate certainly matters. You don't want to speed up if you're trying to slam on the brakes to avoid hitting something. Either is an acceleration, but only one of those is really what you want to do. Now, the units for position and speed and velocity are fairly intuitive, so I didn't pause to discuss them much. But of course, for position, we describe things in units of length, miles or kilometers. And then whenever we put those units over time, we came up with a derived unit of miles per hour, or we could have meters per second, or kilometers per second, kilometers per hour, some sort of unit of length over time. Well, let's look at the units for acceleration. So we know that it is defined as velocity over time, and velocity is defined as displacement over time. So we have displacement over time over time. And those actually combine. Dividing by something twice is the same as dividing by that thing squared. So this is really like displacement over time squared. And we're typically going to be using meters per second squared. That is meters per second. And let's look at a quick example to maybe interpret that a little more clearly. So if your velocity changes from 25 meters per second to 30 meters per second over the course of 1 second, what is your acceleration? Well, let's look at it. Acceleration, which is given by the letter A, is defined as the change in velocity over time. Well, the same delta we've seen before means change, and it means final minus initial, no matter what quantity you're talking about. So change in velocity is final velocity minus initial velocity. Well, our final velocity was 30 meters per second. That is what we accelerated up to. Our initial velocity was 25 meters per second. So final minus initial, 30 meters per second minus 25 meters per second, shows us a change in velocity of 5 meters per second. And similarly, our change in time is our final time minus the initial time. We know it took 1 second, so we end our final time at 1 second. Our initial time is 0 seconds. 1 minus 0 is 1 second. Now, I'm very often, pretty much from here on out, going to drop the delta off of the t, because we are sort of going to assume that we start measuring from a time of 0, and anything minus 0, of course, is itself So rather than carry around an extra piece of notation, I'm going to save some ink, save some paper, and we'll just write t for time. It is just implied that you start measuring from 0. And of course, you don't need to subtract off 0. All right, so we've got our two amounts. We now put those together. Our acceleration then, change in velocity, we changed 5 meters per second. We gained 5 meters per second over the course of 1 second. So 5 meters per second per 1 second. 5 meters per second in 1 second gives us 5 meters per second squared. We added 5 meters per second in 1 second. That is how to interpret acceleration. It is how much your velocity changes per unit time. All right, now let's consider various situations because this is where acceleration and velocity get tricky. When velocity and acceleration are in the same direction, that is, their vectors are pointing in the same direction, your speed goes up. If you're driving forward and you accelerate forward, just like in this previous example, your speed is going to go upwards. The total amount of how fast you're going goes up. Well, just like going forward and accelerating forward cause your speed to go up, you could be moving backwards and accelerating backwards. Well, then you're going to speed up, in this sense, in the negative direction. So your speed, since it's the absolute value, is just going to go up, but your velocity would be negative and getting more negative. Alternatively, whenever your acceleration and velocity are in opposite directions, speed goes down. That is, if you're moving forward and you have an acceleration that is backwards, for instance, moving forward while hitting the brakes, your speed is going to go down. But you could also have the opposite situation, where you're moving backwards, so you've got a negative velocity, but you're starting to push the car forwards. Well, that's going to cause your speed to slow down again. You're going to have a negative velocity that's becoming less negative. In both cases, the velocity should be going towards 0 if they're in opposite directions. And I've broken it down into a little sort of Punnett square here. So this is what happens to your speed. If you have a positive velocity, positive acceleration, speed goes up. Negative velocity, negative acceleration, speed will also go up. If you mix them, for instance, positive velocity, negative acceleration, your speed is going to go down. Or a negative velocity with a positive acceleration will also cause your overall speed to go down. And that's usually fairly intuitive. It's a little maybe weird at first glance, but once you think about it, it starts to make sense. And as we begin to work examples and problems, these things will become even more clear. And I think that's when you really get a true understanding of this material. All right, now before we move on to graphing, I want to just introduce a little bit more vocabulary. So these things might already be intuitive to you, but let's just make this as clear as we possibly can. So anytime I use words like constant or uniform or steady, that means no change, and that means change in direction or magnitude. These things are staying the same. If I have a constant velocity, I'm going straight in one direction at the same speed, and it's not changing. Same goes if I phrased it with uniform velocity or a steady velocity. Those all have the same meanings. And when you go to read word problems, you need to start identifying these sorts of key words that might have some hidden information in them. But I will stress that more when we start problem solving. Additionally, the opposite of that would be a variable speed or variable position. If it's something that is variable, it of course can undergo changes in direction or magnitude. It might be speeding up or slowing down, or as I mentioned, it might be turning. We'll get to that later on. For now, we're going to keep things in straight lines, moving either left or right or up or down. We will eventually get to two-dimensional motion, where things can actually turn off into a whole new direction. All right, and one last caveat before we close this video and begin our videos on graphing. I want to make the point to say we are always going to work with constant accelerations in this class. That's not always the case in the big wide world. Things can certainly be much more complicated. But we're going to work with constant accelerations. And there's some physics pun to be made here. The change in acceleration is actually called a jerk. So I could make the joke there's no jerks in this class. And again, I sorry I didn't warn you to put down your drink. Hopefully you didn't spit your water all over your computer screen. But all right, anyway, those are the little bits of vocabulary I'd like you to know or to watch out for. And one last caveat, that our accelerations will always be constant to keep things a little simpler in this class. All right, well, I will see you guys next time as we begin to talk about motion diagrams and graphing some of these variables that we have been discussing. Take care.